This is going to be midterm number 1 review. In Econ today, we are focusing on the trade-off between two goods, x1 and x2. You can think of it as x and y, x2 being our y, but in 10A we're going to use x1 and x2, and those represent our two goods, and we're only focusing on two goods. We want to choose the optimal consumption bundle, that x1 and x2, that will maximize our utility. That's the measure of happiness or satisfaction that you get from consuming these two goods. It will come out as a number, and that measures how much happiness these goods gave you. So, as a consumer, we will buy the best bundle of goods determined by our preferences that we can afford, which is determined by our budget. Here is our budget constraint. It is P1x1 plus P2x2 equals M. P1 and P2 being our prices and M being our income. In 10A, we want to spend all of our income on these two goods only. If we were to draw this budget constraint, it'd be this downward sloping line, and this slope is called the price ratio, which is negative P1 over P2. The reason that it's negative is because it is this downward slope. Over here on the x1 intercept, we have M over P1, and that means we're spending all of our income M on x1, so we just divide it by P1. Same idea with x2 over here, but it's going to be M over P2. Then we have four main preferences that we focus on, which are Cobb-Douglas, perfect substitutes, perfect complements, and quasi-linear. You could also see satiation and bats, and I have a couple of examples about those. So our first preference is Cobb-Douglas, our well-behaved preference. If we were to draw it over here, we know that pink line is our budget constraint, and then this curved line, it's called a convex shape, is called our utility curve, also called the indifference curve. The reason that it's called an indifference curve is because we are indifferent between all the points on this curve. Indifferent meaning we have no preference between them. They all give us the same level of utility. The slope of this curve is called our MRS, and that's going to be the negative marginal utility of x1 divided by the marginal utility of x2. Where the budget constraint and the utility curve meet is called our tangency point right here, and that's where our optimal consumption bundle is. This is where the slope of the budget constraint equals the slope of the indifference curve. We know the slope of our indifference curve is the MRS, and that's going to be the negative marginal utility of x1 over x2. And then the slope of our budget constraint is that price ratio, which is the negative P1 over P2. With Cobb-Douglas, we have diminishing MRS. That just means that up here, our slope is pretty steep, and then it gets smaller and smaller and smaller, so we have a decreasing slope, a diminishing MRS. That just means that the more and more of x1 that we have over here, the less and less of x2 we are willing to give up. And that is because with Cobb-Douglas, we prefer averages to extremes. We prefer a balanced consumption. I like to think of it as buying new clothes. Let's say you lost your luggage on a trip. Would you rather have 9 shirts and 1 pair of pants, or like 6 shirts and 4 pants? You probably would rather have 6 and 4, so we want a balanced bundle. For our midterm example for Cobb-Douglas, this is what a Cobb-Douglas utility function looks like. We can see that there's two inputs, that x1 and x2, and the output of our function will be the level of utility that we get from these two goods. We know it's Cobb-Douglas because they both have an exponent attached to them, and they're being multiplied by one another. So we just plug in a value for x1, we plug in a value for x2, our optimal bundle, and out will come our utility level. So for this one from winter 24, we have Ricardo is consuming apples, which are x1, and bananas, which are x2. So it won't always be x1 and x2, but it will always be two goods. Here is our utility function, and we see it's a Cobb-Douglas because they both have exponents and they're being multiplied by one another. Then we see apples cost $2 each. I recommend, as you see info when you're reading the question on your midterm, just write it down. That way you don't have to go back to the question and look. And he has $60 in income. How many apples does Ricardo consume in his optimal bundle? So there will always be 2 steps for all the preferences. For Cobb-Douglas, our first step is to set the MRS equal to the price ratio, because this is where the two slopes are equal. This is where our tangency point is going to be on the graph. So MRS, we know, is going to be the marginal utility of x1 over the marginal utility of x2, and the price ratio is that P1 over P2. The reason I put them both as positives is because if they're both negatives, I can just multiply or divide by -1. So to make it more simple, I'm just going to set them equal to each other as positives. Shortcut to get the MRS and Cobb-Douglas only is you can do C over D times x2 over x1. In this case, we knew that our C was equal to 1/3 and our D was equal to 2/3 because C and D are the exponents attached to x1 and x2. So we had that 1/3 here and that 2/3 here. So I have 1/3 over 2/3 times x2 over x1. Once again, I know that I can multiply by the reciprocal here to get rid of this fraction in the denominator. So I'm going to multiply by 3/2. That gets rid of the 3's. And then I'm just left with x2 over 2x1. In this case, we know that our x2 was our b and our x1 was our a. So that's going to be b over 2a for Ricardo. And then we're going to set that MRS equal to our price ratio. So we're going to have b over 2a is equal to that 2 over 4. From here, I just like to cross multiply. So I'm going to have 2a times 2, b times 4. That's going to give me 4a equals 4b. So we know that a equals b. This is helpful because our second step for pretty much all the preferences is to just go ahead and plug it into the budget constraint. Since they are both equal to one another, I'm going to plug in a for both x1 and for x2, and then I can solve for a. So we know the price of 1 was equal to 2 and price of 2 is equal to 4. So we have 2a plus 4a equals that income of 60. And so then we have a is equal to 10. And since a is equal to 10 and b is equal to a, our optimal bundle is going to be at 10, 10. This maximizes our utility, gives us the most happiness. And so our answer would be B. Another shortcut to get the optimal bundle for Cobb-Douglas in lecture slides is going to be optimal amount of x1 equals c over c plus d times m over p1. Remember, c was our exponent attached to x1 and d was our exponent attached to x2. And then you can just multiply it out by the income given, the prices given, and that's going to give you your optimal amount, and you would have gotten 10, 10 again. This part right here specifically, only the exponents, is called our expenditure share. So if they ever ask you about the expenditure share of a good, it means how much income you're spending on that good. And that percentage or fraction can be found using either c over c plus d or d over c plus d, depending on what good they're asking about. Our second preference is called perfect substitutes. This time we have our utility function once again, and we have two goods being added to one another, a being the coefficient next to x1 and b being the coefficient next to x2. A good example of perfect substitutes is Coke or Pepsi. If you just bought a 24 pack of Coke, you probably don't need a 24 pack of Pepsi. You're really indifferent between the two because they're so similar. So you're going to consume all of one good and none of the other. If we were to draw this, we'd have this linear constant slope because these two goods are being added to one another. So you're either going to consume at this intercept where you want all of x2, or at this intercept where we want all of x1, which is great because we already know how to find those intercept values. The slope of this indifference curve is once again called the MRS, but this time it's going to be a divided by b, these being our a and b. So here we have Amy, and she has a utility function of 6x1 plus 12x2. We see that p1 equals 5, p2 equals 8, and she has an income of $80. So this time our step one, instead of setting MRS and price ratio equal, is we are going to compare the MRS and price ratio. So this time, if the MRS is greater than the price ratio, we're going to consume all of x1. If the price ratio is greater than the MRS, we're going to consume all of x2. And that is always consistent. So in this case, we have an MRS of A over B, so that's going to be that 6 over 12. So our MRS is 6 over 12, and then our price ratio is going to be that 5 over 8. We know that 5/8 is greater than 6/12, which is 1/2. So we're going to go ahead and say that the price ratio is greater and we want to consume all of x2. Since we know we want to consume all of x2, we're going to go ahead and set x1 equal to 0, plus our price of 2 was 8, x2 equals that income of 80. That means our optimal amount of x2 is going to be 10, and our optimal bundle is going to be 0, 10. A shortcut for perfect subs is we know when we want x1, we're just going to consume at that intercept. So you can just go ahead and, instead of plugging it into the budget constraint, do your income divided by the price of 1. You want all of x2, you're going to go ahead and do 0, m divided by p2 for your x2. Now for our next preference, we have perfect complements. We know it's a perfect complement whenever we see this min. And on a graph, it looks like this, these L-shaped curves. Basically, our optimal bundle is at these kink points here. I like to think of an example as flashlights and batteries. Let's say that your flashlight takes 4 batteries. Let's say this is flashlights on the X1, this is 4 batteries on the X2. And then let's say over here on this indifference curve, I have 2 flashlights and 4 batteries. This gives me just as much happiness as having 1 flashlight and 4 batteries. I am indifferent. They're on the same indifference curve. Even though I have an extra flashlight and I should be happier, I only have 4 batteries, so I can't even power on this other flashlight. So I'm just as happy. For winter 2017, we have Joe has the utility function. We see that it's a perfect complement because of that min. How many units of good 2 will he use if his income is 19? The P1 is 1 and P2 is 2. So for step 1 of perfect complements, we're actually going to set the 2 things in the parentheses equal to each other. So we have x1 equals x2 plus 1. That's all we're going to do, and that's going to be helpful when we plug in for our budget constraint. I'm going to plug this in for x1 here, because x1 is equal to that. P1 is 1. We know that x1 now equals x2 plus 1. We know that P2 is 2, and our x2 is going to stay there because now we're solving for x2 in our budget constraint since they're both x2, and that's going to equal our income of 19. Just to simplify this out, we have 3x2 equals 18, and x2 optimally is going to equal 6 will be our answer. Some examples about demand. That's where I'm going to go into different types of goods. Normal inferior goods respond to changes in income, while ordinary and Giffen goods respond to changes in prices. So for a normal good, as your M, which is your income, increases, your demand for X1 increases as well. I like to think of this as normal, as it says, because if your income is rising, you're probably going to want to consume more goods. Then for an inferior good, as your income goes up, your demand for that good actually goes down. I like to think of this as fast food. Once we're rich, we're going to be over fast food. We're not going to want it anymore. We're actually going to consume it less. Then when we have prices, as P1 increases for ordinary goods, our demand for that good is actually going to decrease. This is the ordinary thing to happen. As the price goes up, we're probably going to want to consume that good a bit less because it got more expensive and we have less of a desire to buy it now. And then for Giffen, it's the opposite. As prices rise, our demand for that good actually goes up. I like to think of this as a gift because it's Giffen. It kind of sounds the same. And we all know those people who value things that are more expensive. And so maybe you want to go buy something for someone just because it's more expensive. You have more of an incentive to buy it. Notice that for all of them, it's always responding to income or prices going up. And then what happens to X determines what good it is. So as income goes up and X1 goes up, it's going to be normal. And as prices go up and X1 goes down, it's going to be ordinary. And then inferior is the opposite to normal, and Giffen is the opposite to ordinary. We see that this is a perfect complement since we have that min, and we know for the first step of perfect complements, we're just going to set them equal to one another. So x1 equals x2 in this case. They don't have a coefficient next to them, just going to be x1 equals x2. Then we're going to plug this into the budget constraint. So since we know they're both equal, we're going to have p1 x1 plus P2 x1 equals M. In this question, we see they don't give us prices or income, and so we are going to find the demand of that good. That just means that we're finding how much of that good we want, that optimal amount. without having prices and income, we're just going to leave them as variables. So since I see they both have x1 in common, I'm going to do x1 times p1 plus p2 equals m. And then I'm going to divide both of these by p1 plus p2. So we have x1 demand function equals p1 plus p2. So our demand is just leaving the variables in there. And then the question asks us, is this good normal? Is this x1 normal? And so in order to be normal, we see by definition, as income goes up, our demand for that good goes up. So I see if this income is getting bigger on the top, yes, the demand of x1 is going to go up because having a bigger number on the top is going to give us a bigger demand of x1. Is this good ordinary? That means as prices go up, our demand for that good is going to go down. That's the ordinary thing to happen. And so if this price of P1 goes up, what would happen to our demand of X1? Well, if we're dividing by a bigger and bigger number, then we're going to get smaller and smaller and smaller for that demand of X1. So yes, this is an ordinary good. So it's a normal and an ordinary good. Our preference number 4 is quasi-linear. How we know it's a quasi-linear is our utility function will look something like this, where we have one linear component and one non-linear component being added to one another. What you're going to want to do first whenever you see a quasi-linear is you're going to run an MRS test. So you're going to find the MRS, and after you find that MRS, you're going to ask yourself what happens as x1 increases and x2 decreases. That's the test. Depending on the outcome, we're either going to notice it's the diminishing MRS, which means the MRS is getting smaller. And as we know, this means that we have a convex shape. That's a Cobb-Douglas. Averages are preferred to extremes, and we want an interior solution, meaning that we want something along this curve. We're not going to be at the intercept. We want at least one of each good because we prefer balanced consumption. If it's an increasing MRS, it's the exact opposite, where we have extremes preferred to averages, meaning we want these corner solutions, and we have this concave shape. This means we want to consume at one of the intercepts, either m over p1 0 or 0 m over p2, kind of similar to perfect subs. So looking at this example from spring 2023, we see that our MRS is going to be marginal utility of x1 over marginal utility of x2. Here the marginal utility of x1 is just going to be 1, and the marginal utility of x2 is going to be, this is technically 4x to the 1/2. Whenever we see a root, that means x to the 1/2. And so we're going to bring that 1/2 to the front, and then we're going to subtract 1 from the current exponent. So this is going to become 2. And then whenever we have a negative exponent, we know that we can bring this to the top. And so then we're going to have root x2 over 2 as our MRS. Bringing that up here, we see if we're increasing x1, there is no x1, so our MRS stays constant. And then if we're decreasing x2, this is going to get smaller. So we're going to run it like a Cobb-Douglas because it is this diminishing MRS. So since we're solving it like Cobb-Douglas, we already know the first step is to set that MRS equal to the price ratio. So our MRS is here, and then our price ratio is 3 over 1. Set these equal to each other, and we're going to have root x2 equals 6 after cross multiplying. Square both sides to get rid of that root. We have our optimal amount of x2 equals 36. Then we can just go ahead and plug that into the budget constraint, so we know that this is going to be 36. We know that our price of 2 was 1. We know that our price of 1 was 3. And then we're trying to solve for x1 now with an income of 20. After doing that math, you're going to get 3x1 is equal to negative 16 after subtracting this. Since we can't have this be equal to a negative number, we know that we can't consume all 36 of x2 that we desire, and so we're going to consume as many as we possibly can. Since they're priced at $1 each, we're just going to consume 20 of x2 because that's as many as we can afford. So our correct answer would be C. Then we have an increasing MRS example. Here if we have the marginal utility of x1 over the marginal utility of x2, we know we're going to bring that exponent to the front, so we have 2x1, and then for the bottom we're going to have 3x2 and subtract 1 from that current exponent. and that's going to be our MRS. So if we have 2x1 over 3x2, we say what happens as x1 increases and x2 decreases. Well, if x1 is getting bigger and bigger and bigger, and x2 is getting smaller and smaller and smaller, then we have a bigger number in the numerator and a smaller number in the denominator, which means that our MRS is increasing. Now we're going to find our quarter solutions. We know those are going to be m over p1, 0, and 0, m over p2. So it's going to be 20 divided by 2, 0, and 0, 20 divided by 5. Our two bundles that are possible are 10, 0, or 0, 4. And now quasi-linear for increasing MRS has a different step 2 than the rest because we're used to plugging into the budget constraint. Here we're actually going to check the utility at each of these points, and whichever one gives us the higher utility is the one we're going to consume. So since our utility function was this x1 squared plus x2 cubed, we're just going to go ahead and plug 10 in for x1. So then we have 10 squared, and there's no x2, so this utility is going to be 100. And then for this one, we're going to plug in 4 for x2, so we have 4 cubed, and that's going to be 64. And so since this 10, 0 gives us a higher utility, we're going to want to consume 10 of x1, which are our fiddles. Then we have a satiation. Here we see that we have this negative in front of here, and that tells us that the highest possible utility we can have at this point is going to be 0, because any other numbers are going to give us a negative utility, and we don't want that. So basically what we're going to want to do is just zero this whole equation out. So we're going to turn this w into a 3 because 3 minus 3 is 0, this c into a 2, and that means that our utility here would be 0, and that's our highest possible utility. So we're going to want this 3 too. I'm just going to make sure that that is affordable by plugging it into the budget constraint. Budget constraint is usually our step 2. So I'm going to say, okay, wine costs $10, so we want 3 of them. Cheese costs $5, we want 2 of them. That's going to give us 40, and that is within our income of $50. Then we have this preference, which are bads. We see there's a negative in front of this x2, which means that x2 is giving us negative utility. Therefore, we don't want to consume x2 at all. We're only going to consume x1. If we're only consuming x1, we know that's going to be m over p1, 0. Our income is 35 since they gave us that budget constraint, and the price of 1 is 5. So our optimal amount of x1 is going to be 7, and our optimal amount of x2 is going to be 0. Finally, this one says, which of the following could be a demand function? In order to be a demand function, we have to satisfy scale invariance. Invariance means that our demand function does not change when we scale it by a constant. So that means we're scaling P1, P2, and M all by a constant. They use lambda. I'm just going to use the number 2 to make it a little simpler on myself because I'm choosing my own constant. So I'm going to multiply P1, P2, and M all by 2 and see if my demand function stays the same. So for A, we have m squared p2 minus p1 over p2 squared. I'm going to multiply each of these by 2. And then when I simplify this, since this 2 is attached to the m, I'm actually squaring both the m and the 2. So I have 4m squared, 2p2 minus 2p1, all over, same idea here, 4p2 squared. I can simplify this a little bit more because this 2 and 4 can be multiplied by one another since they're attached. So we have 8m squared p2 minus 2p1 over 4p2 squared. Looking at what we have left here, this is not equal to our original demand function. It's quite different. So this one is not a demand function. If I tried out D, I have p2 squared over m squared minus p1 over m. I'm going to multiply each of these by 2. And that's going to simplify to 4p2 squared over 4m squared minus 2p1 minus 2m. I see here that this 4 and this 4 cancel out. this 2 and this 2 cancel out, so I'm just left with p2 squared over m squared minus p1 over m. I see that this is exactly the same as what I started with here, so this one is a demand function. That is all. Thank you so much and good luck.